In a quiet patch of the night sky, a low-frequency radio telescope picked up a heartbeat that theoretically shouldn't exist, 707 pulses every second. The source is PSR J0952-0607A. Black Widow Pulsar, a neutron star so massive and so overspun that it is effectively living on borrowed physics. It siphons material from a tiny companion star, not out of malice, but because extreme angular momentum is the only thing holding it together, the last barrier before it crosses the invisible line, where matter stops being matter. Tonight, this is not cosmic horror. This is a failure analysis case file on the universe's load-bearing limits, spin magnetism, and collapse. So what is actually keeping this star intact? And what happens the instant it slips? A signal like this isn't just a story, it's a measurement. And in high-energy astrophysics, extreme measurements come with extreme consequences. Detected by the LOFAR radio telescope at frequencies usually buried in cosmic noise, PSR J0952-0607 is not an isolated curiosity. It is the first clear data point in a series of stress tests the universe runs on matter itself. Over the next few minutes, we'll examine 3 of those tests. The kinetic limit, where rotation fights gravity. The material limit, where the strongest crust known begins to fracture. And the structural limit, where early stars grew too massive to survive their own design. One calibration before we begin. While the physics here is violent, we are observing it from a calculated safety margin. This is an investigation into the breaking point of matter, not a forecast of our own extinction. Case file open. Our first test begins with rotation. If you want to understand the breaking point of matter, start with He force that is currently counterbalancing gravity rotation. PSR J0952-0607 is not spinning like a planet or a star in any conventional sense. It is behaving like an industrial centrifuge overclocked to the point of catastrophic failure. While a high-speed industrial centrifuge operates at thousands of revolutions per minute, this object completes 707 full rotations every single second. To visualize the mechanical stress involved, consider the surface velocity. The equator of this star is moving at roughly 20% the speed of light. At this velocity, the centrifugal force is so extreme that the star effectively forgets it is supposed to be a sphere and bulges outward at the equator. This is not a gentle spin. It is an extreme kinetic barrier. The rotational kinetic energy stored in this system is estimated to be on the order of 10 to the power of 45 joules. To put that industrial figure into perspective, that is comparable in order of magnitude to the total energy our sun will emit over its entire 10 billion year lifespan, all compressed into a flywheel the size of a city. This immense rotation acts as a structural reinforcement. Gravity wants to crush the star past its neutron-supported structure to complete the final collapse into a black hole, but the centrifugal force pushes back, holding the event horizon at bay. The star is effectively suspended in a state of dynamic tension, surviving only because it never stops moving. But spin doesn't come for free. Where does this system keep getting its fuel? The answer isn't violence, it's geometry, one invisible boundary where gravity leaks. PSR J0952 did not start its life spinning this fast. It is a recycled pulsar, an old machine that has been spun up by an external power source. That source is a companion star, a lightweight object, likely a brown dwarf or a stripped white dwarf, orbiting dangerously close. In this binary system, the gravity of the neutron star distorts the space around its partner. There's a specific mathematical boundary called the Roche lobe, a teardrop-shaped region of influence. Once the companion star's material expands past this boundary, it is no longer gravitationally bound to its parent. It spills over the edge. This process is scientifically termed Roche lobe overflow. It creates a continuous stream of superheated plasma that spirals down onto the neutron star. When this matter strikes the surface, it transfers its angular momentum to the pulsar, kicking it faster and faster, millisecond by millisecond for millions of years. It is more accurately described as a turbine being driven by a high-pressure fuel line. This transfer of mass and momentum is what allowed J0952 to reach 707 Hz. However, this lifeline is also a threat. As it accreted more matter, the pulsar grew heavier. It is now estimated to be 2.35 times the mass of the Sun, the heaviest neutron star ever weighed. And even with the fuel line open, there's still the bigger mystery. Why hasn't the core collapsed? This is where the case file gets controversial. 3 explanations, and none are comfortable. According to standard nuclear physics, neutrons have a limit. The Tolman-Oppenheimer-Volkoff limit suggests that at around 2.1 to 2.3 solar masses, the quantum pressure pushing neutrons apart should fail. Gravity should win. The star should implode. But J0952 is sitting right on or perhaps slightly over that calculated edge. So why is the detector still picking up a signal instead of silence? Hypothesis 1, the stiff equation of state. The most conservative theory suggests our calculations are slightly off. The nuclear matter in the core may be stiffer, meaning harder to compress than current models predict. This added rigidity would allow the star to support a slightly higher mass before structural failure. Hypothesis 2, the hybrid core. Deep inside, the pressure may be so intense that neutrons dissolve into their constituent parts, quarks, forming a hybrid core that offers a new type of resistance against gravity. Hypothesis 3, the strange star. This is the most radical possibility. Some astrophysicists propose that the core has undergone a phase transition into strange quark matter, a soup of up-down and strange quarks. If this hypothesis holds, J0952 may no longer behave like a conventional neutron star approaching the regime of a strange star. A theoretical object that is more stable and compact than neutron matter, allowing it to survive densities that would terminate a normal star. Whatever the internal architecture, one thing is certain. J0952 is a system operating at absolute capacity. It is an anomaly operating at the absolute boundary of the kinetic limit. Rotation buys time, magnetism doesn't. And the next system fails in a completely different way. Meet the strongest crust currently known to physics, built from nuclear matter, not chemistry. If a pulsar is a kinetic anomaly, a magnetar is a magnetic one. These are neutron stars born with magnetic fields so intense, up to 10 to the power of 15 Gauss, that they dominate the star's external environment and plasma dynamics. But the true danger of a magnetar isn't just the field itself. It is the container that has to hold it. The surface of a magnetar is a solid crust on the order of a kilometer thick. But calling it solid is a drastic understatement. In the deep layers of the crust, immense pressure forces atomic nuclei into bizarre semi-fluid arrangements. Physicists classify these phases by their shapes: gnocchi forming dense clumps, spaghetti stretching into long rods, and lasagna flattening into layered sheets. Collectively, these structures are known as nuclear pasta. While the name sounds whimsical, the material properties are sobering. Computer simulations of molecular dynamics suggest that nuclear pasta has an incredibly high breaking strain. In engineering terms, while steel fractures, when deformed by a small fraction of a percent, nuclear pasta may withstand deformation strains greater than 0.1 before failing. This places it among the strongest materials ever modeled by physics, a lattice of neutrons bound by the strong nuclear force, far denser and more rigid than anything found on Earth. This crust acts as a pressure vessel. It traps the star's turbulent magnetic field inside, locking the magnetic lines in place. But magnetic fields are dynamic. They twist, shear, and evolve. Over time, the magnetic pressure builds up from the inside, pushing against the rigid nuclear pasta crust. A war of attrition begins: the magnetic stress versus the material strength. So what does it take to crack the strongest material in the universe? On December 27, 2004, we got a partial answer because the Earth noticed. A wave of gamma radiation washed over our solar system, saturating the detectors of nearly every space telescope in operation. It blinded the Swift satellite and ionized Earth's upper atmosphere, causing it to expand. This wasn't a solar flare. It came from SGR 1806-20, a magnetar located on the other side of the Milky Way. What happened was a starquake. Just as tectonic plates on Earth slipped to release stress, the crust of SGR 18, 0952-0607 finally succumbed to the magnetic torque. The nuclear pasta fractured. The failure was likely microscopic in scale, perhaps a shift of only a few centimeters, but because the material is so dense and the magnetic tension so high, the energy release was catastrophic. When the crust snapped, the magnetic field lines, previously twisted like a coiled spring, suddenly untangled and reconnected outside the star. This event, known as magnetic reconnection, released an intense burst dominated by gamma-ray emission. In just 0.1 seconds, SGR-18-06-20 emitted approximately 2 times 10 to the power of 46 ergs of energy. To put that into a manageable perspective, the magnetar released more energy in order of magnitude than our Sun produces in roughly 150,000 years. This wasn't an explosion of matter, it was an explosion of magnetism. If you had been observing this event from a standard, safe interstellar distance of 10 light-years, the sheer intensity of the flash would have destroyed the ozone layer of your planet, initiating a mass extinction event. If that sounds terrifying, good. Now comes the part that keeps it honest distance and direction. Let's pause the horror for a moment. Physics demands context. While the SGR-1806-20 event was the brightest explosion ever detected from outside our solar system, it did not harm anyone on Earth. The reason is the inverse square law. The magnetar is located roughly 50,000 light-years away. By the time that wave of energy reached us, it had spread out over a sphere so vast that its intensity was reduced to a measurable signal rather than a lethal weapon. Furthermore, magnetar flares are often highly directional. They tend to emit energy in focused beams or jets similar to a lighthouse beam rather than a uniform spherical flash. Unless Earth is staring directly down the barrel of the jet, the risk is significantly lower. We exist in a cosmic standoff distance, a safety margin defined by the sheer emptiness of the galaxy. But to understand the biological limit, we're going to do something safe, you in a simulation with extreme assumptions designed to probe the biological limit rather than predict a real event. VR online. Distance locked 1,000 kilometers. This is a stress test, not a prediction. To truly understand the biological limit, we must step inside the inverse square safety margin. We need to close the gap. We are going to run a simulation that places a human observer inside the lethal proximity of a magnetar. Reality check. Please note that the scenario you are about to experience assumes a specific extreme set of conditions. You are unshielded. The magnetar is active, and you have somehow arrived at a distance where the magnetic field strength exceeds 10 to the power of 14 Gauss. In reality, a human wouldn't survive long enough to observe this environment directly. For this stress test, we will isolate the magnetic effects in a controlled model, treating radiation as out of scope. We are testing the durability of molecular chemistry against one of the strongest magnetic fields known. The subject is you. First, the systems fail, then your senses, then before you can even process it, your instruments overload. Your survival suit is a complex ecosystem of sensors, life support pumps, and communication arrays. As you materialize 1,000 kilometers from the star, the magnetic field lines cut through the copper and gold circuitry of your equipment. According to Faraday's law of induction, a changing magnetic environment induces an electrical current. But here the field is so intense that even small movements can induce destructive currents and voltage transients in the wiring of your suit. The microchips do not just overheat, they are instantly scrambled. The logic gates that process binary code are overwhelmed by magnetic noise. Your HUD, the heads-up display, flares white and then dies. The pump circulating your oxygen seize. There is no explosion, only the sudden heavy silence of a complete technological blackout. You are now drifting in the void, wrapped in dead machinery. With the digital overlay gone, you look out into space with your own eyes. But the optics of space are no longer normal. In our everyday experience, a vacuum is empty and transparent. But quantum electrodynamics, or QED, tells a different story. In the presence of a magnetic field this strong, the empty space becomes a prism. The vacuum becomes polarized. Virtual particles, electrons and positrons, pop in and out of existence, aligning themselves with the magnetic field lines. This phenomenon is called vacuum birefringence. The space around the magnetar acts like a birefringent crystal, splitting light into different polarizations that travel at different speeds. As you look at the stars behind the magnetar, they don't look like points of light. They are smeared, doubled, and distorted as if you are looking through a thick, warped lens, as if you're looking through an anisotropic, warped lens. The universe looks fluid, unstable. The light from the magnetar surface itself is eerie, polarized to nearly 100%, creating a visual texture that the human brain, evolved under the gentle sun of Earth, cannot process. You are seeing the fabric of space-time straining under the load. And once light itself stops behaving, normally biology is next. This is the quietest death in the universe. Phase 3. The chemical breakdown regime. We tend to think of our bodies as solid objects. In reality, we are clouds of atoms held together by the delicate exchange of electrons. These electrons orbit the nucleus of an atom in roughly spherical shapes, and they link hands with neighbors to form covalent bonds. These bonds are the glue of existence. They build water, DNA, proteins, and enzymes. But electricity and magnetism are two sides of the same coin. When you introduce a magnetic field of 10 to the power of 15 Gauss, the electromagnetic interaction is pushed into a regime where magnetic effects dominate atomic structure. At the atomic level, the magnetic pressure begins to squeeze the electron clouds. The comfortable spheres of your atoms are crushed into thin, needle-like cylinders, aligned with the magnetic field lines. This is atomic orbital deformation. Chemistry depends on shape. A key fits a lock because of its shape. Your enzymes process energy because of their shape. Your DNA holds genetic code because of its shape. When your atoms are compressed into needles, the key no longer fits the lock. There is no pain because the neural pathways required to transmit pain signals are dissolving. The sodium and potassium ions that drive your nervous system can no longer flow across cell membranes. The electrical impulses that define your consciousness cease instantly. Then the structural failure begins. The covalent bonds break. The glue simply stops being sticky. Your body does not burn, it loses its definition. You cease to be a biological entity and become a cloud of monatomic dust drifting along the magnetic field lines. This is biological coherence failure. The machine of your body didn't break. The operating assumptions that make chemistry stable no longer apply. Terminate simulation. Back to safety. As the VR fades and the familiar spherical atoms of our safe reality return, we are left with a lingering question. We have seen the kinetic limit of the pulsar and the material limit of the magnetar. These objects are terrifying, yes, but they are also small, mere city-sized remnants. Where did the universe learn to build objects of such extreme density? To find the original blueprint, we have to look much further back in time. Terminate simulation. Now ask the deeper question. Where did the universe learn to build objects like this? To find the original blueprint for these extreme objects, we have to go back to the cosmic dawn. Long before the first neutron star was forged, the universe was experimenting with a different kind of architecture. In the early epoch of the cosmos, roughly 13.5 billion years ago, the universe was filled with pristine clouds of hydrogen and helium, uncontaminated by heavier metals. Without metals to help cool these clouds, they didn't fragment into small stars like our sun. Instead, they collapsed into colossal giants. Current astrophysical models, such as those proposed by Begelman, Voluntari, and Rees, suggest that under these specific conditions, the core of a massive protostar could collapse directly into a black hole without blowing the star apart. The result was a theoretical object known as a quasi-star. If J0952 is a kinetic anomaly, a quasi-star was a structural paradox. It was an inverse star. A normal star fights gravity with nuclear fusion in its core. A quasi-star fought gravity with the sheer radiation pressure of a black hole feeding on it from the inside. Imagine a star the size of our entire solar system, swallowing Saturn's orbit with a surface temperature of only 4,000 Kelvin, glowing a deep, ominous red. But deep inside there was no fusion reactor. There was a feeding engine. The central black hole accreted the star's mass, generating an incredible amount of energy that inflated the outer layers like a hot air balloon. It was a parasitic architecture, the heart of the star, was actively consuming the body that sheltered it. But this design was inherently unsustainable. It was a structural limit that could not be maintained. The black hole would eventually grow too large, or the fuel supply would run dry. The delicate balance, the hydrostatic equilibrium between the crushing weight of the gas and the outward push of the accretion disk, would inevitably fail. A star powered by a black hole is unstable by design, yet it may be the reason galaxies have dark hearts. They died young, so the modern universe could grow old. Quasi-stars were short-lived, likely burning out in just a few million years, a blink of an eye in cosmic time. But their failure was not in vain. When the outer envelope finally dissipated or was fully consumed, what remained was not a typical stellar corpse. It was a black hole seed, a massive object, thousands of times the mass of our Sun, sitting ready in the void. These seeds are the leading suspects in one of astronomy's biggest cold cases, the origin of supermassive black holes. Today we see monsters like TON 618 or Sagittarius A*, anchoring the centers of galaxies. They are too big to have grown from normal star collapse. They needed a head start. The failure of the quasi-stars provided exactly that. They converted the chaotic, massive gas clouds of the early universe into the dense gravitational anchors that would eventually pull galaxies together. In this light, PSR J0952-0607 and the magnetars of today are essentially miniature echoes of those ancient titans. They are modern iterations of the same universal struggle, the war between matter's structure and gravity's ultimate victory. The Black Widow spins to survive. The quasi-star consumed itself to survive. Both are testaments to how far physics can be pushed before it breaks, which means our case isn't just about danger. It's about architecture, what had to fail for us to exist. So should we be worried? After staring into the kinetic fury of a black widow and the magnetic crushing power of a magnetar, fear is a natural biological response. But forensic analysis requires objectivity. The reality is that we exist in a fortunate standoff distance. Space is vast. That vastness is not just empty room. It is our primary shield. The inverse square law ensures that even the most violent outbursts like the SGR 1806-20 flare dilute into harmless signals by the time they cross the galaxy. PSR J0952-0607 is 3,000 light-years away. The nearest known magnetar is thousands of light-years distant. We are not in the blast zone. We are in the observation gallery. We live in a calm suburban neighborhood of the Milky Way, far removed from the high-density industrial zones where these machines tear themselves apart. Safety isn't a miracle. It's a margin measured in light-years. The universe is a system built on failure. If matter never broke, we wouldn't be here. It is only when stars collapse, fracture, and collide that the universe creates its most precious materials. The gold in the circuits of the device you are using to watch this, the uranium heating Earth's core, and even the iodine in your body, these heavy elements were likely forged in the extreme end-state transitions of neutron stars. These extreme systems, the black widows, the magnetars, the ancient quasi-stars, are the foundries of creation. They test the limits of physics so that complexity can exist. The breaking point of matter is often the starting point of life. Case closed for now. Because somewhere in the dark, another signal is ticking toward its own breaking point.